Hello and welcome everybody to another episode of Algorand Developer Office Hours. I'm your host, Ryan Fox, and today I'm thrilled to be joined by one of my colleagues, John Giannotti. He is Head of Applied Research here at Algorand. Good morning to you, John.
Good morning.
We're going to be talking today about the latest release of the Algorand virtual machine, which is version 1.1. That was pushed into or activated in beta net right now. It's going to be activated in the test net tomorrow, and then come Saturday, it will be live and activated on mainnet. So very relevant to what's going on today. Lots of exciting new features in there. John, a warm welcome from Boston to you. Where in the world are you joining us from?
Sort of Boston, about an hour and a half north of Boston in New Hampshire.
Outstanding. Well, we are neighbors by state then. That's wonderful. Well, we're glad that you're here connecting with our Algo fam and specifically our Algorand devs and the creators out there. So I checked out GitHub, and it looks like you've got about 30,000 lines of code contributed to the Go Algorand repository. That's massive.
I'm not sure. I think that probably I refactored some things that other people wrote, and I got credit for it. Have been contributing a lot lately, but I don't know about 30,000 lines. We'll see. I should go look and see if I can figure out how I get credit for so many.
Yeah, nice. Well, I think there were 18,000 deletions as well. So it's
I deleted a lot of code.
Good. Well, we appreciate that. Making things faster and refactoring is always appreciated. So as the head of applied research here at Algorand, can you tell us a little bit about what that means, and then what do you get to do on a daily basis?
Yeah, it's an unusual position. We take the applied and the research part pretty seriously. So I start every morning by meeting with the research team. These are cryptographers, theorists, distributed systems experts, and think about the sort of far future of Algorand. And then I spend the rest of my day talking to developers and writing code. So the applied part of that research. So I try to take as many ideas as I can from the far future and bring them to the near future, and get them into Algorand.
Nice. That's great. Well, I know, but you seem like you're always available to the devs, either in Discord or certainly within GitHub, answering questions, answering issues. It's outstanding. So we appreciate all of your contributions. Well, what brought you to Algorand? How did you end up getting here?
Yeah, so I was let's see, I was a faculty at Brown University. I taught networking, distributed systems, software engineering classes. I had started to taper off that work because I had a small startup company in a very different space. I sold that company, and then while I was rooting around for the next interesting thing to do, one of my colleagues from Brown, Morris Hurley, who's in the theory group here at Algorand, approached me and said, "Hey, we're doing cool stuff at Algorand. Would you like to be involved?" And I had actually noticed Algorand before and thought I was really impressed by the people. And so with the explicit invite, I certainly had to check it out. And so that's how I got here about a year and a half ago.
Outstanding. Well, we're glad you're here. It's been awesome. And today we're going to talk to the devs about what's in the latest release, in that AVM 1.1, as we like to call it. So in that release, can you tell us what you are most excited about?
So for me, the big thing is contract-to-contract calls, which are interesting in their own right. But what really, to my mind, what makes them, why I'm excited about them is because I feel like we've now properly rounded out inner transactions. Inner transactions are what we added in order to feel like we had an AVM 1.0. So that was about middle of the year. No, toward the end of last year. And but they were missing a couple things that we knew were a little harder and needed more time to get right. And in particular, that's contract-to-contract calls. So AVM code that's calling more AVM code. We knew that required a lot more thought and care than just allowing things like payments and asset transfers. So I feel as though this is where I feel it's more, to my mind, this is more like complete, because you can now do everything with very few exceptions. You can do everything in a transaction that you could have done at the top level from SDKs. So I think that's quite interesting. And I think you can write better, more secure, simpler contracts that way. So I'm excited about that.
Yeah, absolutely. Well, from the expandability part of things, like so what is this intertransaction and this contract to contract calling? If you combine those things together, like what are the devs now able to do that this
Yeah,
1.1 has introduced?
gotcha. I think the main thing is where 1.0 really made things easier to do some of the stuff people were already doing. 1.1, where you can do app-to-app calls, really enables a new kind of activity, and that is that one smart contract on Algorand can interact with another smart contract on Algorand. Previously, if two smart contracts, if you wanted to build it that involved multiple smart contracts, then a lot of the work was going to be done off chain. You were going to have the DApp interact with one smart contract, learn something, compute something, and then supply it to the second smart contract. And you could sometimes, if you're very clever, you could get some of that to happen atomically using our atomic transaction groups. But roughly speaking, people didn't do that because people wrote apps to be isolated little universes. And app-to-app calling really first makes it possible for an app to call another app. Let's say it can call an Oracle or it can call an AMM to exchange something, and then do something else with the result. And because it enables it, it also encourages people to start writing composable contracts that you can interactively work with. So I think that's the way I always say it. It sounds a little tech bro, but like it enables an ecosystem of apps instead of just individually cool apps, because they can actually interact with other.
Well, great. Well, I know you've got some cool demos. That's really what the focus of the Office Hours program is all about here. So, are you ready to get started showing us some code and
Yeah,
showing us what's in there?
yeah, absolutely. What I wanted to do was I wanted to start with um, what the AVM 1.0 sort of allows, and then talk about how 1.1 expands upon that. So I first wanted to sort of remind everybody or tell people for the first time that the reason we introduced intertransactions, the first set of intertransaction things in 1.0, was to make it possible for apps to create effects instead of what they did before, which was approve effects. What does that really mean? That doesn't sound all that different. So it used to be that to build in the Algorand ecosystem, you used a combination of apps and logic sigs. Logic sigs could hold assets and had real permissions over accounts, and apps did not. Apps could only operate in their own, manipulate their own internal state. And that doesn't sound very powerful, but where the power came was by combining them together. Because you could have an app decide whether something was a good idea to do, and the logic sig would then allow it to happen because the logic sig actually had the permission. These were powerful ideas, and you could combine them together using our atomic transaction groups, but it's a little challenging to do it perfectly. Because you had to, the caller of these sorts of apps would build complicated transaction groups, and then the app had to look at the transaction group and decide, is this correct? Did my caller set everything up perfectly? And I can now say, yes, that's correct. Just do it. That's much harder to write. It's much harder to write a program that's at an action and determines whether it's exactly correct, or maybe it's doing something subtle that you didn't even look at. So for example, Algorand has a closed to field. Closed to field is a very powerful field. Sends all of your assets to somebody. So your app had to be sure to check that, even if it didn't expect callers to ever use it. Had to check to make sure they didn't. So what 1.0 did is it combined apps and power authority over an account into one package. And so now an app itself has authority over an account. And then the question becomes, well, how does it exercise that authority? How do you submit a transaction from an app? And the answer is you don't. You call the app, and the app creates those transactions internally. And because the app created them and the app has authority over the account, transaction processing allows that to go through. And so you can imagine why it's much easier to write an app that does the thing that you want it to do instead of looking at transactions and checking to make sure that they're exactly correct. Looking at transactions that someone else created. So that's what 1.0 did. And I think that's seen some nice uptake. I've read a lot of our Most well-known projects are beginning to build or have already begun building that way, so to simplify their lives a bit. And so the next question is, well, what couldn't you quite do? Let's see. First, I'll show you some of that code so that you have in your head what an app could do as of 1.0. So the simplest example is an AMM, automatic market maker. So I'm going to show you a really simple automatic market maker. I wouldn't really call it much of a market maker at all. Maybe an automatic token swapper. And the idea of of an AMM usually is to hold two assets, called X and Y, and a real AMM figures out how much X you ought to get if you supply it with some Y, or if you supply it with some X, it gives you some Y. Our market maker is simpler than that. It just swaps. So if you give it 5X, it will give you 5Y. If you give it 5Y, it will give you 5X. Obviously, that means it can run out of tokens. There's all sorts of this isn't a very useful app, but you can see sort of in one place where you might instead calculate a ratio and so on. And so you can see how this works and why we think it's simpler than 0. So we're looking at version 5. It's a little tricky because it's a little bit like Java but class files and Java version numbers. The AVM version number and the teal version number are disjoint. So the teal version number just increments one by one each time. So AVM 1.0 is teal version 5. So this is a version 5 program that's going to allow us to use inner transactions. So some of this is the kind of boilerplate you see in every app, even before inner transactions. The first thing you do is you figure out whether this is the initial creation of the app or not. If it's the initial creation, we jump down to create, and I'm going to suppose that you tell this app, hey, you are going to hold these two ASA IDs. I'm going to, in application arg0, I'm going to put an integer, big endian encoded, because that's how I always do it in algorithm. And I'm going to put that in global state under the key X. And the second argument, I'm going to put that in global state under the key Y. So this only happens when you create this AMM, when you first install the app. Okay, if it's not a create, then, well, the other piece of boilerplate is that some apps want to be updatable in case bugs are found. So this, I just wanted to show you a common thing you would see in these sorts of apps. You check if someone's trying to update or delete the app. And in my case, I allow it if the creator is the one doing it. So if the person who installed this app is the one who sent this transaction, then I allow an update or a delete. Not terribly important. And this is where, if you wanted to be an immutable app, you would just error out if these completions are set to update or to delete at all. Otherwise, we have the usual case. It's a little funny that it's called no op, because the no op means don't do anything except call this app, no additional operation. So if it's a no op, that means it's a normal call. We're going to head down here. We're going to look at our first application arg, and you can see that I'm trying to show you a little bit, very little, how to make your contracts ABI compliant. So it used to be the sorts of conventions for how you would call an app. Some people would put a word in the first application arg and then switch off of that. Some people would, since they knew it was only going to do two or three different things, depending on the number of application args, it would decide what to do. So that's the kind of independent decisions that doesn't lead to an interactive ecosystem of apps, because the apps don't know how to call each other because there's no standard convention. We are defining that convention, and we call it the ABI. And according to the ABI standard says that the way you decide which of your operations to call is by taking the signature of the operation, hashing it, taking the first 4 bytes, and using that as the thing you switch off of. That's kind of abstracted away by a pseudo op called method. So this thing is really saying is the first application arg, the first 4 bytes of the hash of this thing. And the only operation that this AMM supports is swap. So I then assert that that's true. So if you're calling this my simplistic AMM, you had better be calling swap, because that's the only thing you can do. So now I handled the swap. Now I'm showing something else that I'd like to see more of, but it's admittedly somewhat more complex. And that is that I'm not going to assume. So what is this, by the way, what does the signature mean? It means, because AXFR is a special type that is the name of a transaction type, an asset transfer. This means that this, again, this is according to the ABI spec, this contract is saying, I expect that you're going to call me as a pair of with a pair of transactions in a transaction group, where the previous transaction is an AXFR, and I am the next transaction, the app call itself. And so the contract goes on to check that. It looks at its own group index of the app call itself, subtracts 1, keeps track of that number because it's going to need it a lot. And then it starts checking this stuff that it expects. Oops, sorry. So this is saying, let's look at the slot behind me because I subtracted 1. And let's make sure that it's an AXFR. It better be. If it isn't, die. So I'm inserting that. Then check that AXFR is a payment to me. What does me mean here? It means the current application. So as I said, 1.0 brought applications and authority together. And so that means that every application has an address that it has authority over. And so the way a swapper contract expects to work is that the first AXFR is a payment to the contract itself. Okay. Then there's some checking to say, so you did an AXFR to me. What did you send me? Did you send me the thing that I put in global state X? If you did, then I'm going to give you some Y. So look up Y. This is looking it up in global state, and then go do the swap, because I'm putting the ID of Y on the stack, and then I'm going into the swap code. If you didn't give me X, let's see if you gave me some Y, because you're supposed to give me one or the other. So now I grab the asset ID again, and I say, is it equal to the thing that I put in my Y global state? Here I assert if it's not true, because at this point, there's nothing else it should be. In fact, if we got thrifty, then we were given Y. And so I put X on it. So the point is, at the end of here or here, I have the asset that I would like to return to the caller. And now we get to see how you actually do that within a transaction. So I'm in the do swap. I say that I'd like to, you basically build up an inner transaction almost exactly the way you would build up a transaction from an SDK, because you can fill out all of the important fields to fill out. You don't need things like first value and stuff. So you say, I'd like to begin a new transaction. I'd like to set ITXN field is how you set a field. So the first thing I'm going to do here is I'm going to set the XFR asset field. That's what asset is I'm going to transfer. Recall that I put the app ID, either X or Y, on the stack already. So it's sitting there on the stack. And so I've got a new transaction. And so far, the only field set in it is the transfer asset. And I didn't even actually specify that this transaction was going to be an XFR yet. That's what this does. This specifies that I've got an XFR. Then here's where I say that this AMM is a particularly simplistic AMM. It just gets the asset amount. If I was given 5 X's, this sets the inner transaction asset amount to 5. So it's going to put out 5 Ys. So somewhat boring. Who's it going to send it to? Well, it's going to send it to the sender. Whoever paid me the asset, that's who's going to get the other asset. That makes sense. Then this is something a little bit tricky that helps answer Jonathan Gomez's question about what's a good convention for how we handle fees. So because these inner transactions consume the same sorts of resources that outer transactions do, there are fees associated with them, the same min fees as associated with top-level transactions. And who pays those fees? Well, just as a top-level transaction, the sender pays the fee. Here, the sender, again, pays the fee. Who's the sender? It's the app account. So the app account actually needs some algos in order to pay fees, unless another addition that I think was in 1.0, but might have been even before that, is that we now allow fees to be pooled. So a previous transaction can overpay, allowing a later transaction to not pay. So this app is taking advantage of that. And the documentation for this app, it would specify, if you intend to call me with an extra fee already paid. One extra min fee should have been allocated, should have been paid in the top level transactions. And so that means there's a credit. And so this app is in essence refusing to pay a fee on behalf of the caller. It's the caller's job instead. So this is one easy way to do this, Jonathan. You just don't do it. It's kind of bail out of this. You say, hey, the way this app works is it's going to cause inner transactions on your behalf. Hey, I'm doing it on your behalf. You pay those min fees. You put those extra fees in the top level transactions. So I won't have to hold on to algos in the app then I submit the transaction, and this should pay the caller. So now let's go to 1.1. So let's suppose, when I said I was going to build an ecosystem, or that this allows building an ecosystem of apps, what's an example of that? Well, imagine that soon, Algorand's going to have, looks like 5 or 6 AMMs out there. Now, at first, I bet they all have very different interfaces, but as the ABI becomes more popular, I hope and expect that they will begin to offer the same interfaces to callers. And once they do, it will be possible to build, let's call them AMMs or order routers that know how to invoke each of the various AMMs to find out what the best price is and send your order to that. So you send your X to this router program. The router program checks and figures out which of the underlying AMMs to actually call. That's the sort of thing you can do in 1.1. So let's talk a little bit about what we needed to add to make that possible. So first, in a very straightforward way, we had to make it legal to make these sorts of calls. So here, where we set the type of the transaction, APPL, Apple, I like to say Apple, it's shortification, of course. We just disallowed that as of 1.0. You weren't allowed to do an application call. So we had to allow that. And similarly, we had to let you set all the transaction fields of an application call, things like application args, things like the foreign accounts array, the foreign assets array, and so on. So we had to just mechanically allow you to do it, sure. But there's another complexity that we needed to add, and that is, notice that as is true of most interesting Algorand applications, this AMM it's not just a simple call this app and something will occur. It is call this app in this particular transaction group configuration. There has to be an AXFR followed by an app. Now, inner transactions as of 1.0 didn't work that way. You could submit one transaction at a time, and they didn't seem to need this ability to put 2 of them together, because all inner transactions are always atomic with respect to all transactions, including the inner transactions, are always atomic with respect to the whole group. So if any one of them ever fails, all of the effects of the entire transaction group are torn down. So we already had atomicity. We didn't need to combine transactions. But notice that this AMM looks around in its trace group and tries to find the AXFR that paid it so that it can decide how much to pay out. So that means that if you want to be able to call apps, you need to be able to call apps on their terms. You need to be able to set up transaction groups that look like what they expect. And so that's one of the things that we needed to add as well. So the ability to not just create inner transactions, but create entire inner transaction groups. I think it's kind of nice that what fell out of that design is essentially just one new opcode, ITXN next. So let's move over to my router. This is a function call. So this starts an inner transaction, and I'm trying to call that AMM that I just described to you. So I just showed you the interface to it. How would an app call this app? Well, it would start by ITXN begin. I'm about to create an inner transaction. Then it would, there was some setup here to make sure that the ID of the app I intend to call, the inner AMM, is already on the stack. In fact, it's on the stack twice. So just keep that in mind as this runs. I first use app params get to find given an app ID, what is the address of that? How can I send it algo? Well, in this case, send it assets, ASAs. So app params get actually returns two values. First, it tells you whether or not it was even there, and then it gives you the value. So first, I assert that it was there, and so I get the app address, and I set the asset receiver for my inner transaction. I'm going to try to pay into this inner AMM. I set the type. Again, pay into it. I'm giving an asset transfer. And then I send it the exact same asset that was sent to me. Remember, I'm just a router app. Whatever they sent me in the previous transaction in an transfer, I'm going to send to the underlying. Here, I'm doing something much dumber than a real application would do. Rather than figure out which AMM to send it to, I'm going to send half to the first AMM and half to the other. So I'm actually just going to send half of the asset here. So I set the asset amount to half. And I probably should also, for example, confirm that I was given an even amount of the assets so that there's nothing being lost. I use the same trick of setting the inner fee to 0 as saying, callers, if you intend to call me, then you had better do so with the fees already paid. Then I use ITN next. That's the new opcode that allows you to not just submit a transaction as soon as you build it, but instead move on to building the next transaction. And only after you've built up all the transactions you need to build, then submit them all. So remember how the AMM worked. It expected an AXFR and then an app call. So we've got the AXFR. Now let's build the app call. So set the type to APPL. Set the first application arg to the first 4 bytes of this hash. This is just the sort of way Ruby works. Then, and this part is a little tricky, and is probably the thing that people are going to stumble over the most when working with inner app calls. Recall that Algorand has always required that when you make an app call, if it intends to look at ASAs or look at other apps or look at other accounts, balances on other accounts, you needed to specify with these 3 arrays. I call them all the foreign arrays, the foreign resource arrays, even though the accounts array doesn't have the word foreign on it in the source code, but it doesn't matter. There are these 3 sorts of resources that if your app intends to look at, you must specify them in the transaction. The same thing is true of inner transactions. I have to tell, I'm calling an inner transaction, I have to pass on my right. I have the right to access this asset because I barely mentioned this, but that AMM would have required you to specify the asset in the foreign asset array when calling the app. So I'm demonstrating how I would pass on that information, that right. So I take the asset out of my assets array. This assets array is why this app can access the asset, and I add it to the assets field of the transaction that I'm building. The way ITXN field works on array fields is that each time you call it, it pushes another item onto that array. So if I needed to pass 2, I would have called ITXN field assets again with another one. Prepay, and then I submit. And this should actually be, let's say, because this is I didn't show you this code, but the idea was that I was calling this inner AMM thing twice, once with A and once with B. And just as in the previous code, I set up these global variables A and B to contain some IDs, in this case of the inner AMMs. So so we're seeing most of what you need in order to get inner transactions working. I've mentioned that a little bit, that you can pool fees across transactions, and that works down into inner transactions as well. As I mentioned and showed you here, that you often in a transaction will set its fee to be 0 as a way to enforce that app doesn't have to pay the fees, and the top level callers need to have done that already. I think that's the easiest one to understand. The next thing that's a little tricky to understand, or the next thing that's pooled, it's called the opcode budget. So in order for Algorand to maintain its scalability, we have a rule that says that these transactions can only execute opcodes that will cost a certain amount of CPU time. Calling things like hash functions and signature verification functions is expensive. And so you can't run too many of them inside of an app call. You can add and subtract quite a bit. Anyway, the budget is 700 per app call. It used to be that each app call got exactly a 700 budget. But that's pretty annoying if, for example, you want to call 2 apps. The first one does very little work. The second one does a lot of work. You might ask, yes, Algrand, I know you want to be scalable, but since I did such a small amount of work in my first call, can't I do a little extra in my second call? And the answer is yes now. So the app code budget is pooled across transactions so that if you have 4 app calls in your top level actions, you get 2,800 app code budget to be spent across all 4. That's what Jonathan asked about earlier. He's packing some extra, pretty much empty app call transactions in his at the top level, so that he can run a little bit more in one of his transactions where he does the real work. The reason I know he's doing it at the top level is because as of 1.0, that's all you could do. But as of 1.1, you can do something really clever, which is since you can make app calls anytime you want now, apps can call apps. One thing you could do if you're running out of CPU, if you're running out of app code budget, you can call a tiny app that you already built it and set it aside, and it really just returns 1 pretty much. There's some caveats there. But that's roughly an extra 700 of opcode budget. So you can sort of, in some sense, gas up as you go, and you need more opcode budget. This is not the easiest thing to manage. We want to be very clear about that. But it does sort of keep the rules fair. Every transaction gets only 700 opcode budget. And we know, I now sort of think of transactions as the indivisible quantum, the individual quanta of computation on Algorand. And so if you want to do more work, you have to tell us you need more of these. So that's something that you can do to increase opcode budget as you run, as long as you have the fees to pay for it. And then the third thing that's pooled in some sense now is the number of inner app calls you can make. So you may have been wondering, so if I have a lot of apples, can I just call inner apps forever inside of a transaction and install the blockchain? And the answer is no, you cannot do that. And that is prevented by what it used to be, as of 1.0, that each application could make up to 16 inner transactions. But those were simple inner transactions. They were pages and transfers. Remember, we didn't have app calls. The rule could not be that every app gets to call 16 inner transactions anymore, because if it did, if that was the rule, you could branch out and make an infinite number of app calls. So now the rule is in some ways simpler. Your entire transaction group, regardless of its size, can have up to 256 inner transactions inside of it total, no matter whether they're app calls, asset transfers, etc. So that's another way where we've sort of pooled what you could have done before. With 16 app calls, you could each have 16 underneath it. So to get 256, so now you can the rule is simply that you can get 256 total app calls. So those are 3 things that are tied to pooling. But I want to go over the sort of trivial opcodes that we added, because we don't want to forget to tell you about some stuff that's in 1.1. I feel like I've covered the high level. All right, so a couple of other things that were added. Just as we didn't allow app calls before, we also didn't allow key reg transactions. Those were the 2 kinds of transactions that weren't allowed. The reason we didn't allow key reg is because we thought that's pretty weird. An app would register participation keys. But the more we thought about it, the more we realized that actually makes a lot of sense. Apps may represent DAOs. So if an app is a DAO, if people have contributed funds to an app ID, an app out there that they perhaps they possess voting tokens in order to tell it to do what it wants to do and so on. It may very well be that there's a lot of assets tied up there, a lot of algos maybe, and they may want to participate in governance, not governance, consensus. And now you can do that. So if the app allows it, the app can send a key reg transaction on behalf of an authorized caller, and then once you've key regged, you can use those in consensus. That was sort of just, it was sort of untidy that we didn't allow it. So why not? I hope to see people using it someday. The other thing that we allow, which is, again, we previously just disallowed this out of an abundance of caution. But as we thought about it more and ensured ourselves that we weren't opening up a bad something dangerous, we realized that rekeying is a very powerful feature that we wanted to allow apps to do. So we previously would not let you set the rekey field on a transaction. Somewhat surprising, but every single transaction in Algorand has a rekey field that if you want to, when you submit the transaction, you can simultaneously rekey the account to a new sender. And even in Zero, we allowed an interesting thing, which is you could rekey an account to the app address of some app. If you did that, then the app suddenly has authority not just its own account, but also the account that you're rekeyed to the app. But we didn't allow the app to set the rekey field, and so therefore the app couldn't rekey it back to you. And it turns out that there's a really cool pattern that we wanted to allow that requires exactly what I just described. And that pattern is that sometimes you need to supply an extra account or extra space for an app to operate on your behalf. And so there's a cool pattern where you, before you interact with the app, you create an account and opt it into the app. So the app can now store things inside that account. And then you kind of hand over the account to the app by rekeying it to the app and saying, hey, here's the extra storage that you need in order to service my needs. And the app says, thank you very much, and keeps track of it, and has a new place to store information. But it's always a good sign of good design if after building up something complicated like that, you can, using the proper sequence, tear them back down. And without rekey, you can't tear that back down. The app can't rekey the account back to you when you're done using the app and let you reclaim your algos that were held up in the minimum balance. So by allowing apps to rekey, they can give it back. There's also there's an even cooler technique that is enabled, where in a transaction group, you could rekey your account to an app and then unrekey it at the end from the app. And that would give the app the authority over your account for just the duration of the transaction. So this is a pretty powerful technique that I would not recommend using willy-nilly, but it does enable the rare instance of a situation where you want to give an app authority over a user account. We explicitly did not make that easy to do because we don't think that that's something that you normally want to do. We don't want to have users to understand and read every line of a contract in order to have any confidence that their algos aren't going to get stolen. So under normal circumstances, contracts have authority over their own account, and everything else has to sort of flow through that. Couple rules that I haven't covered that inter-app calls can go 8 deep. We don't think there's much need for more than that. App calls cannot make inter-app calls to themselves, even through indirection. So app A can't call app B, who calls app A. This is a huge source of bugs in the Ethereum ecosystem. It's called re-entrancy. It's very hard to write programs that might be called while they're in the midst of running. One of the few things about blockchains that make them simpler is that they are extremely sequential. And re-entrancy basically brings the same kinds of bugs that you see in multi-threaded programs. Suddenly you see them in blockchain programs as well, which is pretty annoying to throw that source of errors back into the world. So we do not allow re-entrancy.
Okay, so on that last point there, you were talking about re-entrance. How does Algorand guarantee that there is no re-entry?
Yeah, so it turned out to be very simple to make this guarantee. It's not that it's the Ethereum ecosystem. If they wanted to, they could change the rule tomorrow. They just it's hard to change things that have been set. So the rule is very easily enforced at the app call site. We walk up the chain and we say, what are all the apps that are sort of, it's just it's a call stack like almost like any programming language. And we just look at the call stack to see if the app ID that you're about to call is already on the call stack. If it is, then you fail. So it's pretty straightforward. It's just that no one thought of this in the early Ethereum world, right? Well, it's a tricky bug. It's the bug that caused the split between Ethereum and Ethereum Classic.
That's true.
But it still shows up once in a while.
All right. Well, that's a very important one, and I think that just demonstrates why Algorand is a very safe language to use, and we're always thinking about those edge cases and making sure that we're trying to mitigate or protect against those types of issues with the programming language. So, well, that's good. I mean, you covered a lot. You talked briefly about the ABI, and the ABI was introduced in 1.0, but we're seeing definitely more tooling within the SDKs now, being able to make use and generate these ABIs. But you talked about that spec. Like where do we want to direct people to find that spec?
I can probably post the link, but if you search for Algorand, well, we keep them in the Algorand Foundation repo. So when I say we here, now I'm sort of colloquially speaking we, because now it's the Algorand Foundation. There's a separation there. So we contribute to those specs, but they're not under Algorand Inc.'s control. And so on GitHub, it would be Algorand Foundation /ARC. That's ARCs, capital ARC, lowercase s. And it's ARC4. So the ARC4 spec is an ABI spec. The ARC3 spec is an NFT spec. And there are a lot more of them that are in progress. But ARC4, you should be able to go for that pretty easily.
Absolutely. Algorand ARC4, and that is on GitHub, and the organization name is Algorand Foundation. All right, good. Well, thanks for that. So, I mean, we talked a lot about, what is in 1.1 that's out there today. As we talked about, it's activated already in BetaNet. So if you have applications ready to go, you can do it there. Tomorrow it will activate on testnet, and then on Saturday it will activate on mainnet. And of course, always, if you are using the Algorand sandbox tool, you can run it as dev mode, and you would always have the latest version, so you can always do that locally. So that's what's coming up. So you can use this code, you can use all these examples that John went through here today, and you can use them today. Can we get out your crystal ball and look ahead? Like what are you excited about next? What are you working on now?
Yeah, so I think the let's see, the most interesting thing, the thing that maybe causes the most trouble for complicated contracts today is how to manage global state. So in fact, that trick I mentioned earlier about rekeying an account into the app, that's something like a trick around global state. That's a way of giving more state to the application. Right now, the way Algorand works is that you have global state, which is up to 64 key value pairs. Plus, you have, in a sense, you have one single big map from every account to some more states, 16 key value pairs. And that works really well for when you need to store information about users. And so they can opt in, and that gives the app extra state. But it doesn't work so well when you need to store sort of information about random stuff, like you want to store transaction IDs forever because you want to prevent replay attacks or something like that. So that's important for bridging applications. So Algorand needs a way to let you acquire extra state as an app on demand. And I think that's our highest priority, figuring out what the right way to fit that into the existing Algorand programming model, fee structure, and so on. And so we expect to figure that out sometime soon. Similarly, there's a related problem, which is it's a little bit challenging. I mentioned to everyone the rules about foreign assets and accounts and so on. And that's a rule that allows, in part, responsible for Algorand's extensive scalability, high transaction throughput. I think if you'll investigate other chains that have high transaction throughput, you'll find similar rules. However, it can be a little challenging. I would like to, for example, write an app that handles NFT commissions in the following way. It looks at an ASA, finds out who the current owner is, or the current manager address, and when that NFT gets transferred, it gets transferred with an app that forces you to pay a commission off to the other side. Right now, that's a little bit. You have to do a little bit of indirection to make that work. You can do it, But you can't simply, an app can't simply look up a value on chain and then use that value as, for example, the recipient of a token. It has to have pre-declared, I intend to send this token to this recipient. So that's something that we'd like to improve. I don't think, well, we can't maintain scalability and just throw the doors wide open to this kind of program behavior, but I think we probably can allow a bit of this kind of interaction, and that's usually enough for, we think it will be enough for a lot of interesting apps to be simplified a great deal. So that's something we want to see, and we're hoping to support randomness, at least in some ways, for gaming and so on. It's a little bit more complex than simply make an opcode that returns a random number, because that would be a pseudo-random number that is deterministic and has all sorts of problems. But we're designing a system that would allow higher quality randomness to be available.
And to be available accessible within the teal language.
Exactly. Although not in one call, it would be in sort of in multiple calls. You sort of commit to when you're going to need the randomness, and then you get the randomness later.
Got it.
And finally, within teal or the AVM, we need to add some support to help you build up the kinds of strings that are ABI encodings, because now that apps can call apps, one of the things they need to do is obey the ABI. So the app needs to construct these encodings, and constructing these encodings can be challenging in a stack-based assembly language. So with a few extra opcodes, we can simplify that pain a little bit.
Awesome. Well, John, incredible demos that you provided for us, and great insights into what you're working on in the future. We really appreciate your time here today. Remind us, how do we get connected with you? How do we stay connected to you?
If you have a question that you think anyone else would have any interest in hearing about, ask me on Twitter at Jannotti, and that's JANNOTTI. That's also my Twitter handle. If you have questions that are really sort of inside baseball, and you're having trouble with a teal app, I'm often on Discord. I think you'll probably drop the link to our Discord. I mostly monitor the teal, the PyTeal, a couple other channels. So ask in the right channel, and I will try to answer.
Outstanding. Well, thank you once again, John. Really appreciate your time joining us here on Algorand Developer Office Hours. We hope to have you back in the future.
All right. Yeah.
All right. Thanks, everybody, and have fun building on Algorand.